All right, welcome back for another example, and that's going to be probably the last video of this term. Okay, so let's call this pole placement and state feedback. The third part, and we will simply cover another example. Okay, so this is a 3x3 system with state feedback and not in controllable canonical form. Okay, let's consider our system. The system's going to be x dot equals, we will have a 3x3 system matrix, 1 1 0 0 0 1 and 2 minus 5 4 times x plus 0 0 1 times u, and y is equal to 3 1 0 times x. Okay. The question tells us design a state feedback rule u is equal to r minus kx such that all poles, all closed loop system poles are located at S1, 2, 3 is equal to minus 1. So we want to make all closed loop poles located at minus 1. Okay, so let's take a look at how we can proceed solving that problem. Let's go with the same way. Okay, so let's first take a look at the desired characteristic equation. Q desired of S is equal to S plus 1 cube, and that's going to be S cube plus 3S squared plus 3S plus 1. So this is our desired characteristic equation. What about the closed loop system matrix? Due to, let me break that. Due to state feedback, the system matrix will be modified, and that's going to become A tilde is equal to A minus BK, and that's going to be equal to A matrix, which is at the top over here, right? 1 1 0 1 1 0 0 0 1 2 minus 5 and 4 minus multiplication of b with k. Since the b vector here only have a 1 at the last row, all the matrix entries will be 0 except the last row, which will be composed of k1, k2 and k3. So this matrix will become simply 1 1 0. Sorry, let me give a little more space. 1 1 0 0 0 1, and over here we will have simply 2 minus k1 minus 5 minus k2 and 4 minus K3. Okay. So that's our matrix. Now, what's going to be the characteristic equation comes from determinant of Q of S will be equal to the determinant of Si minus A tilde. Okay, so you will check that this Si minus A tilde, sorry about the tilde, will be equal to S minus 1, minus 1, 0. Okay, there's a minus sign here. 0, S minus 1, 0, S minus 1. K1 minus 2, K2 plus 5, and S plus K3 minus 4. Now I forgot something. What is that? Basically, I forgot to check that the system is completely controllable. That is important to check because basically it's easier to check that than to solve the state feedback problem. And if the system turns out to be completely controllable, that actually guarantees a solution for you. So let me do that. So, okay, let's check the complete controllability. The controllability matrix Q is equal to, for a third order system, B, AB, A square B. Okay. Now let's first calculate A square. Okay, A square matrix, you can just simply multiply A with itself to find the square of that. Okay. 2 minus 5, 4. 1, 1, 0. 0, 0, 1. 2 minus 5 and 4. Okay. It's easier to write the matrix twice because you know that when you're multiplying two matrices, you need to go by a row and a column to find the corresponding entry. For example, this first entry at 1, 1 is 1 times 1 plus 1 times 0 plus 0 times 2, so that is equal to 1. Okay. Similarly, if you make all the corresponding row column multiplications, you will find the square of that matrix as 2 minus 5 and 4. And you can always check this by using a tool like MATLAB, okay, whether you have the correct calculation. Okay. So that is A square. So let's also calculate A times B. A times B is the multiplication of the A matrix with the B vector, and you will get 0, 1, and 4. And you will also calculate A square B, which will turn out to be 1, 4, and 11. Okay? So we need to calculate the determinant of Q, which is the determinant of a matrix that is 0, 0, 1. Sorry, let's start with the columns, right? 0, 0, 1, which is the B vector. 0, 1, 4, which is our AB matrix. And 1, 4, 11 is our A square B matrix. Okay, now you need to also know how to calculate determinants of 3 by 3 matrices. Okay, notes, review determinants for 3 by 3 matrices. In fact, method to calculate determinants for larger matrices follow the same rules, but here we will show one. Okay, so remember that you can do this by selecting a row or a column. Usually you select the one that's going to make it easier. You label signs in a checkerboard pattern. Okay, and over here this is going to be equal to plus 0 times the determinant of this submatrix over here. When you select this entry, you need to calculate this sub-entry, but since it's multiplied with 0, we will not need to do that. 4, 11. Okay, this is also a determinant, a sub-determinant. Minus 0 times the sub-determinant, that's going to be obtained by hiding this, sorry about that. Basically hiding this this column and row. So this is going to be 0, 1, 4, 11. And the only non-zero, so this is equal to 0, this is equal to 0. The only non-zero entry comes from the last entry, plus 1 times, okay? You will have a determinant that is 0, 1, 1, and 4. Okay? So that's going to be equal to 0 times 4, so plus 1 times 0 times 4 minus 1 times 1. Okay, so this is 0 minus 1 multiplied with plus 1 is equal to minus 1. Okay, so that is simply not equal to 0. Okay, so determinant of Q is not equal to 0, so Q is non-singular. Okay, so that is the check for complete controllability. So continue with our problem. So we have basically a desired characteristic equation, and we have the Si minus A tilde matrix. Okay, so we have Q desired of S is equal to Q of S. What was our Q desired of S? Was equal to S cube. Okay, let me first calculate this Q of S. That is equal to simply the determinant of Si minus A tilde matrix. Okay, now let's also calculate the determinant of Si minus A tilde matrix. Remember what that matrix was. So determinant of, so that is S minus 1, minus 1, 0, 0, S minus 1, and K minus K1 minus 2, K2 plus 5, and S plus K3 minus 4. Again, we can basically do the same kind of determinant calculation. Let me show you how that works. Okay, so this is, you see there is a plus here, there is a minus, plus, minus. Let's pick this row to calculate the determinant on, because it already has a 0 entry here. So this 0 entry will not do anything, but we will have plus S times the determinant of hiding this column and row. So we will have s minus 1, 0, k1 minus 2, and s plus k3 minus 4. So that's one subdeterminant. And plus 1 times y plus, because I have a minus 1 here, another minus here, minus minus plus. And then I will basically have another submatrix here, s minus 1, minus 1, k1 minus 2, and k2 plus 5. Okay. So what is that? So this means that Q of S will be equal to S times S square. We need to find this determinant, plus K3 minus 5S minus K3 minus 4. Minus 0, because we have a 0 entry over here, plus the second determinant here, which is K2 plus 5 K2 plus 5 times S minus K2 plus 5, and simply plus K1 minus 2, plus K1 minus 2, because we have this multiplication minus this multiplication, and we already have a minus sign here. Okay. So when we regroup that, okay, you expand and regroup the same powers of S, you will get simply S cube plus, and you will check that please for me, K3 minus 5 times S squared plus K2 minus K3 plus 9 times S plus K1 minus K2, K1 minus K2 minus 7. Okay, so that is our Q of S. And that Q of S has to be equal to Q desired of S, which is equal to, remember that is equal to S cubed plus 3S squared plus 3S plus 1. Okay, in this case we're kind of lucky because at least you see one of the equations that's going to be generated will only include one of the k's, so it's going to be relatively easy to solve these equations. So let's start with that. K3 minus 5 has to be equal to 3, and that means that we can readily calculate K3 out of the box. Okay, let's consider the second equation. We have K2 minus K3 with K3 known plus 9 has to be equal to 3. We have K3 is equal to 8, so K2 minus 8 plus 9 is equal to 3. So we have plus 1 here. So we will have K2 is equal to 2. So that gave us the second coefficient as well. Okay, remember this is basically small k. Okay, and finally the last equation says K1 minus K2 minus 7 has to be equal to 1. We already know K2, so K1 minus 2 minus 7 is equal to 1. So we have minus 9 here and plus 1 over here, so K1 actually comes out to be 10. Okay, so that means the K vector which is composed of these three coefficients, is equal to 10, 2, and 8. So what is the control law? The resulting control law will be a state feedback. So U will be equal to R minus K times X, and that is equal to R times, is equal to R minus 10 times X1 minus 2 times X2 and minus 8 times X3. Okay, so if you apply to the system a feedback from the states having these coefficients, this will result in a closed loop system with all the closed loop poles located at -1. Okay, so I hope that so let me summarize what we have. Okay, so what we have seen basically is that if you construct state feedback law, which is U is equal to R minus KX, the system's A matrix becomes modified and becomes simply A minus BK. And that changes the location of the closed loop poles. But we can actually calculate what the gains should be, such that the new locations of the closed loop poles actually matches a number of desired locations for those poles. And this is called pole placement using state feedback. It's a very powerful method of designing controllers, provided that the system representation is actually controllable, completely controllable, and also the states of the system are actually available to you. Okay, what is the catch? Representation states should be available to the controller. What if states are not available? States are not available. So that is for your senior year, okay? But just to have an idea, is that you need to design an observer, okay? You need a completely observable system, completely observable representation, plus a system, an auxiliary system called an observer. Okay, so these will be covered in detail in EE302, EE306 in your coming year, if you're interested in control theory more than what we have covered thus far. So guys, it's been a difficult spring term for sure. A term to remember, I guess, for all of us. And thank you guys for basically being able to still hang on, and hopefully all of you will have a successful term. But this is the end of our lecture content for this term. Good luck to you all, and hopefully see you next year in some other control courses.